And I don't know, we were all stunned. It was a beautiful lecture, and it was such a cool idea. And it's, the title, I guess the title is public, that it's Poisson's equation almost everywhere. Anand and Aditya and I were working on applications of, basically Poisson's equation approximation for nonlinear filtering as well as optimal control. And this was a completely new take on it. And I just learned, so I made a joke yesterday that if I have an idea, I'm really excited about it. I can go to Peter's website and find out that he did it last week.
Everybody, not just you.
So I'm sorry to say, Amir, from now on you have to go to Peter's website, because I just learned that Peter Glynn is working on something very similar to numerical approximations to Poisson's equation on a fixed alphabet. So even though we're on all of our ends, can I approximate just on a fixed number of points? Well, yeah, I know you haven't been scooped, Amir, don't panic. but it is remarkable how universal this is.
Yeah.
So there's 3 talks. So part of the point of this is that there was just from Amir's talk last year and energy that was already bubbling under the surface, it created all sorts of new ideas and collaborations, which is just, really just what you want from a workshop. So it's just quite exciting for me. So, here.
Okay. So much pressure. Thanks for giving me the opportunity to talk. So I'm going to talk about numerical solutions to the Poisson equation. I'm going to present 2 methods, and I'm going to provide some error analysis where variance trade-off can be seen. So this is joint work with my advisor Prashant Mehta and Sean Mang. Okay. So this is so we are interested in numerical solutions to that PDE, which we call Poisson equation. So rho is a probability density function, h is a real valued function, and h hat is the mean of h with respect to rho, and phi is the solution that we are looking at. So in the case where rho is constant, it reduces to the classical Poisson equation. And that's the mean zero condition we require so that it guarantees the uniqueness of the solution. So specifically, we are looking at this problem. We are given n particles, x1 through xn, that are sampled IID from the probability distribution rho, and we are interested to find a gradient of phi, the solution to the Poisson equation, evaluated at particle locations, x1 through xn. So the challenge here is that we don't know the probability distribution rho explicitly. We are only given n samples from rho, and we are interested to find that. So this is almost like a statistical learning problem. There also you have training data from some unknown probability distribution, and you want to find some hidden function like a classifier. Okay, the motivation to study this Poisson equation comes from nonlinear filtering and feedback particle filter. So in this slide, I'm going to briefly describe feedback particle filter by making comparison to Kalman filter. So in Kalman filter, the system is linear. The state has linear dynamics. The observation is also related to the state linearly. In filtering, we are interested in the posterior distribution, the conditional distribution of the state given history of observation. So in the linear setting, given a Gaussian prior, the posterior distribution is also Gaussian, where mean and variance are evolving according to Kalman filter equations. So feedback particle filter can be interpreted as a generalization of Kalman filter for the nonlinear setting. So there, the dynamics on observation are nonlinear. In the nonlinear setting, there is no closed form solution for the posterior, so the posterior is approximated with the empirical distribution of the particles, where particles are evolving according to this stochastic differential equation. So note that both equations have a feedback structure, a gain multiplied by innovation error. So gain here is the Kalman gain, but the gain here is hard to compute. It comes from the solution to the Poisson equation, and that's why we are interested in the Poisson equation. So here are some examples. So if you have a Gaussian distribution and your observation function h is linear, then phi is linear and grad phi is a constant equal to Kalman gain. So that would imply that the feedback particle filter reduces to Kalman filter in the Gaussian setting. But in general, non-Gaussian setting, there is no explicit solution for the gain. So here, I have a bimodal distribution. The shaded area is the probability distribution, and the solid line is the gain, grad phi. So grad phi in this case is nonlinear, and it's hard to compute. And the objective is to find numerical ways to compute that given only samples from the distribution. So Poisson equation appears a lot in the literature. So here's a definition. The operator on the left-hand side is called the weighted Laplacian, and we use that notation. So weighted Laplacian has been studied as a generator for Markov diffusion operators. The associated heat kernel is also well studied. In the context of a stochastic analysis, Poisson equation identifies the value function. It also identifies the MCMC simulation variance, and also weighted Laplacian also appears in the statistical learning wherever graph Laplacian methods are used. So where it is shown that graph Laplacian matrix is a discretization, can be interpreted as a discretization of the weighted Laplacian. So in the limit, graph Laplacian matrix would converge to the weighted Laplacian. So corresponding to these three branches of literature, I'm going to present three formulations of the Poisson equation. So first one is the weak formulation, which comes from a PDE perspective. So it's obtained by multiplying both sides of the Poisson equation by a test function, and then integrating with respect to rho and doing integration by parts. So here I'm using the inner product notation. So this formulation would lead to a numerical algorithm called Galerkin. So next slide, I will describe this in more detail. The second formulation is based on semigroup. So by the definition of the semigroup, you can rewrite the Poisson equation in this way, which is a fixed point equation. So this would lead to a kernel-based algorithm to solve the Poisson equation. And the third formulation is a variation formulation, where you can also show that the solution phi is a minimizer of the following objective function. If you take the first order optimality condition, it's the Poisson equation. This is the third formulation. So P stands for PDE, or how Poisson views the problem. S is the stochastic analysis, how Sean views the problem, and this is the formulation that they both ignore. So potentially, this is like a learning problem, so you can use our learning algorithms to solve this. But in this,
hopefully, right?
So in this presentation, I'm going to just talk about Galerkin and kernel-based. Okay, so this is the Galerkin. So this is the strong form of the Poisson equation. If you multiply both sides by a test function and do integration and integrate it with respect to rho and do integration by parts, you get this identity which should hold for all functions in this function space. This is the Sobolev space, a space of functions that are square integrable, and also their weak derivative is also square integrable. So this is the infinite dimensional space. So in Galerkin approximation, you replace this infinite dimensional space with a finite dimensional space, where S is just the span of some basis functions. And in the next approximation, you approximate the integrals here by empirical averages with respect to the samples that you have, with respect to the particles. So this would be a finite dimensional equation, and you can go ahead and solve. So from algorithmic perspective, first you go and find a set of basis functions. Then you write your solution as a linear combination of the basis functions. And then you obtain a linear system of equations which you need to solve, where A and B are obtained according to these formulas, which are just in terms of the particles. So I'm going to use this Galerkin approximation to solve, to apply to the bimodal distribution problem. So here I'm using a Galerkin with polynomial basis functions, polynomial up to degree 1, 3, and 5. And this is the result. So the challenges in Galerkin approximation is the choice of basis functions. There is no systematic way to choose the basis functions, and there is no guarantee that your matrix A is well behaved or not. And also, it doesn't scale well with the dimension of the problem. So now I'm going, okay, so this slide is error analysis for the Galerkin approximation. In general, it is very hard to do numerical error analysis, but in the special case, if you choose your basis functions to be the eigenfunctions of the weighted Laplacian, you can do something. So you can write the total error in two terms, bias and variance. Bias is due to the choice of basis functions that you have. If you have more basis functions, it's smaller, and the variance scales as 1 over square root of n, and it also increases as you have more and more basis functions. So there's this trade-off with how many basis functions that you want. The more you have, variance would increase, but the bias would decrease. And this is just numerical simulations. So in the large n, the bias dominates. So as you have more basis functions, the error is lower, but in the low end regime, it's all mixed. Okay, so now the second method, the kernel-based method. So that was the Poisson equation we were interested in. This is the weighted Laplacian notation. So by definition of the semigroup, you have this identity here, and using this identity, you can write the Poisson equation in this fixed point form. So H tilde is defined as follows. Then if you assume that the semigroup admits the kernel, then you can write the semigroup in terms of the kernel in integral form. And finally, you can approximate this integral in terms of your samples, your particles. And this is potentially a finite dimensional equation, and you can solve it. But the problem is that the kernel is not explicitly known. So in the next slide, I would provide a way to approximate this kernel. Okay, so in the special case where you have the uniform distribution, Lebesgue measure, then the associated kernel is just the Gaussian kernel, the heat kernel. But in general case, there is no explicit form, so we use this approximation that was introduced in the literature. The approximation is in terms of the Gaussian kernel, and there is also n epsilon, which just normalizes such that the operator becomes a Markov operator. So this approximation holds in the regime where epsilon is small. And finally, given this integral with respect to rho, you can approximate it in terms of particles. And again, you have the normalization constant such that it becomes a Markov operator. So using this approximation, you can provide a numerical algorithm, which I'm going to describe here. So this was the Poisson equation, exactly. Phi is the exact solution. Then use approximation. You approximate the semigroup in terms of the operator that was introduced in the previous slide. And you also approximate this H tilde by epsilon h minus h hat, because when epsilon is small, it equals its integrand evaluated at 0. Then in numerics, you just evaluate this equation at particle locations. You will obtain n equations. N is the number of particles, and you just need to solve this linear system. It's hard to invert T because it's a n by n matrix, so you just do iteration. And because T is a Markov matrix which has all positive entries, you're guaranteed that it would converge. And because you at the end you're interested in the gradient, you just take the gradient of this and obtain a form for your gradient. Okay, so again, the bimodal distribution example, I applied the kernel-based algorithm for different values of epsilon. And so as you see, as epsilon is decreasing, the solution becomes more and more accurate. But after some point, for very small values of epsilon, the solution becomes irregular. So there is some optimum epsilon. So compared to the Galerkin algorithm, there is no singularity here. Your solution always, it's stable, does something, and it can also be easily extended to manifolds, because what you need is just some distance between the particles, and you can obtain better error bounds, and computationally it scales with n squared, where n is the number of particles. So in the low dimensional problems, it may not be good, but for high dimensional problems, it may be preferable. So this is the error analysis slide. So the results so far are all just for bounded domain. In bounded domain, you can also show that the total error has two sources, bias and variance. Bias scales with epsilon, and variance scales as square root of n. So this is an example, again, where n is high, the bias error is dominating. So in this slide, I'm changing n for different values of epsilon. In this slide, I'm studying as a function of the dimension of the problem. This is for a fixed n. So here, you see as epsilon is changing, this is the error. So the dimension doesn't change the error for high values of epsilon. But for small values of epsilon, here's the plot. These two plots. So for one example, for the bimodal distribution example, we just add dimension, just add Gaussian noise, right? So
Just as my question also, when you look at things as a function of dimension, you have to think carefully about how the problem instance is changing the function of dimension. What is it that you are controlling as p goes to infinity? Like it's not the same Laplacian operator as b, is the row fixed, or what does it mean when you send b to infinity in a problem like this?
So I guess in this example, what I'm doing is I have this bimodal distribution in one dimension, and just add just independent Gaussians in.
Product measure?
Yeah, product. Yeah. Just Gaussian product, because I want to compare with the exact solution. So I need to have some exact solution. So exact solution can be only obtained in one dimension, and if you do just product, it doesn't change anything. Or you can also do Gaussian. So you have also explicit solution for Gaussian, but in Gaussian, you cannot see exactly, the behavior of the error. So this plot is just this plot from 0 to this point, just in the log-like form. So it shows how dimension is changing how error is varying with epsilon. So I guess that's it. So thank you.
Questions?
So is this related to the fact that you use Laplacian? Is that related to the fact that you have SDEs? There's sort of a standard paradigm of SDEs over short time scales, basically, or look like Brownian motion with frozen drift and frozen volatility?
Maybe, I don't know. You mean the approximation that we get?
Yeah, because there are other sort of refinements that you can do beyond sort of standard Brownian motion. You can sort of pick up additional short time asymptotic drifts.
Mm-hmm.
Oh, no, but it's not a misunderstanding. Because, it works as a really nice approximation for the Langevin diffusion and nothing else. So it's, what's here again? So it's a really nice Taylor series approximation between the Langevin semigroup and this funky semigroup.
But the fact that the V kernel was a transient or null recurrent, the Langevin is positive recurrent is?
Well, this is a twisted heat kernel. It's twisted by the square root of p,
Is that?
and only works for one-joint diffusion.
Are you asking for small epsilon?
Oh, yes, I'm sure. And there's a lot of stuff here that's really interesting.
But you go back to the formula for
It was hard to sort of pick up in real time what
Yeah,
the,
absolutely.
why this approximation.
Take a look at the modified, the strange, take the heat kernel, you twist on the right by the density on the left by the square root of the density.
Yeah.
So, I mean, the PEE that you get when you put the non-constant rho in, is that the generator of the diffusion itself, or is that?
Yes. Yes.
So what? Okay. Is that a recurrent diffusion?
Yes.
It's wonderful. Now look,
Yeah.
the right-hand side is not a symmetric for a diffusion. It's a wonderful, it satisfies Taghvaei conditions as a discrete Markov chain. Right? So it has similar properties to the Langevin diffusion. But it's not a symmetry. It's not a symmetry. The T epsilon.
Yeah. This T epsilon is not the same.
Yeah.
The T epsilon. Yeah.
But it's often the case, I don't know that there's any connection, but at least in the numerical solution of STEs for a standard, a paradigm that people follow is that solutions to STEs look locally Brownian. Right?
Mhm.
There's a lot of things that you get out of that insight. And the fact that you're using a Gaussian
Kernel is
just sort of wondering whether there's any.
Oh, but it's not a Gaussian kernel.
It's this is a Gaussian kernel.
Yeah.
It just
Rho is bimodal. But this is a But yeah, but that. Okay, I guess we need to move on. All right. So, thank you.